Alright, this is Mr. McMurray, and hopefully things are recording. I have this bad feeling it might not be, but we're going to hope it is. Hope springs eternal, alright? Despite how much past evidence may not support that hope. Okay, anyhow, here we go. Let's see here. So we should have gotten down scientific method notes through, at least through that, I believe. Let's try again. Metric base units, okay? And in particular, now we talk about time and seconds and how they change that. And finally now it's a atomic clock where you have a cesium-133 atom that gives off radiation at a given frequency, and that frequency is exactly 1 second. And so it keeps very, very accurate and good time. Now, the next thing is length. Length is measured in meters. Meters is a little m. There's also other things. Little m, it can mean milli, so millimeters would be little m, little m. Mass is also a little m, so you have to be careful with little m sometimes, but in this case it's a meter, which is slightly longer than a yard. A yard is 36 inches, a meter is about 39. And so that is the official measurement of length, or distance, if you will. So there you go. Now, originally, when they first did this, they had just gotten figured out the distance from the North Pole to the equator, and how big around the world was and all that. Whew, that's not a very good drawing, but it's pretty good considering. Okay, and they knew the distance from the North Pole to the equator, and it just turned out that if you did about 1/10,000,000th of that, then it would be exactly what we call a meter. Okay, so a meter was 1/10 million of the distance from the equator to the North Pole. Now, that's not a real accessible measurement for most of us. We can't, let's go check that and measure that distance and then divide it by 10 million and figure out how long a meter is. It's not the best, but it was they thought, well, the Earth doesn't change, it's going to be the same size. Okay, well, there's several problems. One is we got better measuring methods that it turns out that it wasn't exactly 10 million meters from the equator to the North Pole, and also, like I said, just not a very good way of measuring that as a standard. So they said, hey, let's try something else. And they said, let's get a physical thing that is exactly 1 meter long. Okay, so you have this little meter stick, basically. All right, but if you have a wooden meter stick like we do, it can get chipped, it can warp. See, mine warped right there. Okay, and warped and broken, whatever. So they need something very durable, and so they eventually came up with a bar made out of metal, the hardest metal they could find, which is platinum iridium. You don't hear about iridium much, but platinum iridium alloys, those two metals combined together. And they keep this in Paris, and that was the official bar, that was the official meter for the world. Now, they made copies and put them in some other places so other nations would have official ones in their places too, but the world standard is the one in Paris. Alright, now, to be honest, I think they should have left it there, but scientists want something that never changes. You still got a bar, and even though it's pretty sturdy and stuff, something could still happen to it. So, they said, we want something that never changes. And one of the things that we think is this, we call it the speed limit of the universe, because we think that's as fast as anything can go, is the speed of light. And so they said, let's define this in terms of speed of light. Light can go 300 million meters in a second. So, they said, a second is officially the distance that light in a vacuum, outer space for example, not through air, travels in 1/299,792,458 of a second. Okay, basically about 1/300,000,000th of a second. Okay. Now, once again, is that a very practical measurement? No, but it is the same no matter what, anytime in the world. So that is the official definition of a meter now. They still have, I believe, the bars in Paris and various countries, but this is the official definition of one. Okay, to me, you've kind of gone backwards to one that's really not very practical, but they didn't ask me, so there you go. And it is a more permanent, always will be the same no matter what. All right, the next base unit we're talking about are kilograms, or mass. interesting, mass is that it has the only unit, kilogram, that is has a prefix in front of it. Kilo means 1,000. Probably because a gram is a very small weight. Okay, just be a little sliver of metal, and it'd be easy to make mistakes on it or be a little bit off. So it's easier to make a kilogram, which is 2.2 pound piece of metal, that is exactly the right mass, and so you can be more precise with that. And so that's probably why they picked the kilogram for that. All right. Now, mass is always measured on a balance. Okay, you have some kind of thing in the middle here. Whoops, not very good there, but okay. And you have a pan over here, and you have a pan over here, and you put something on this side, and you put something on this side, and then when they balance, that tells you that they have the same mass on both sides. And so you put a set of weights over here, and then that tells you exactly how many grams when it balances on this side. Okay, a triple beam balance is a little modified, but you still have a pan, you set your weight on, and you move other weights over here until it balances. All right, scales, on the other hand, which measure weight, are something like this, where you step on it. Oops, this is your feet. Okay, you step on it and it tells you how much you weigh. What its weight is measuring is how much gravity is pushing down on you against the scale. If you go to the supermarket and you get apples, you put them in the scale, it pulls down on the scale, and gravity pulls it down and it tells you the weight. Okay, the problem with weight is that it depends on gravity. So if you go to the moon where there's less gravity, then your weight would change. Now, your mass, on the other hand, does not change, and if you took this balance up to the moon, this side would weigh less, but this side would weigh equally less, and it would still balance, and you would still get the reading of the same mass. Okay, and so we say that mass doesn't change, weight does, and that's true because weight depends upon gravity. However, if you're on the Earth, pretty much the gravity's the same. It has to do with how far you are from the center of the Earth. So if here's the center of the Earth, if you were on Mount Everest, which at this scale wouldn't even be a little bump, but if it was 5 miles high, if you were on top of that, you're technically a little bit farther from the center of the Earth, and you might weigh a fourth of a pound, maybe half a pound less. Okay, it's not much. So pretty much on Earth, gravity is the same. As long as you're on the surface of the Earth, gravity is the same. And so if you increase the mass, it's going to increase the weight. And so they're not the same, but they are related. So if you double the mass, you're going to double the weight. Okay? And since we're on Earth, we can make scales. We have little spring scales that we hang things on, and they have a little hook at the bottom here, kind of like a fish weigher. And they will have grams on one side, and they will have weight or pounds on the other side. And they can do that because on Earth, we know that if it has this much mass, we know what the gravity is, and we can calculate how much weight it will have. And so they may have grams or ounces, grams or pounds or whatever. Okay, and so we can do that, and that scale will be accurate as long as you're on Earth. If you went to the moon, can't use that scale anymore. I have to get a new scale. All right, so yeah, so that's it. Now, the official measurement for kilograms is just a mass of a metal that won't react much, platinum, iridium, fancy that again. Cylinder. It's kept at a controlled temperature and humidity in Paris, and so it will always weigh this or have the same amount of mass or matter in it. And so that is the official measurement of mass. Okay. All right. If you want to pause, write that down. We're going to go to the next page, or maybe we won't. Let's see here. There we go. All right. Temperature. Temperature, normally we think of the metric system, we think of degrees Celsius, okay? That's what we would use in the classroom, okay? But technically the official measurement is Kelvin, all right? So let's talk about Celsius for a little bit, and then we'll talk about how Kelvin came into the picture. Kelvin's the newer temperature, all right? The original idea was that they want to set up a scale that goes from 0 to 100. Okay, and they said, let's make 0 where water freezes, and let's put 100 at water boiling. So if you had a blank thermometer, okay, you could stick it in some water here. Whoops, that's not working very good. Hang on. Okay. you have some water, you stick your thermometer in it, and you could mark where it was when it was in ice or frozen water, and then you could boil the water and mark where that is, and then you could mark it off into 100 little marks. In fact, when I was growing up, Celsius was sometimes called centigrade. Centa means 100, like a century, and grade just means little markings. So there were 100 little markings between 0 and 100. Okay, there's another system set up the same way, which is called Fahrenheit, which is what we use still for the most part in this country. And he went from 0 to 100. His 0 was even colder than freezing of water. He said, well, if we get ice and put salt on it and a little bit of water, it will get really, really cold, kind of like when you make homemade ice cream freezer. Okay, and so it will actually get colder than that. And so he made that his 0 degrees. And he made his 100 degrees human body temperature because he said, well, everybody has a body, so they can take their temperature and they'll know where that is. And a couple problems. One is they had to go back and do some recalculations to a scale. And so instead of our temperature, body temperature being a nice even 100, now it's 98.6, which is kind of an odd number, you feel like. He originally designed it so it would be 100 even, but like I said, they had to recalculate some things and it messed it up a little bit. Also, everywhere on Earth has water or there's living things, and so they probably figured this was a good scale because everybody has access to water and can freeze it or boil it and set up their own ruler to scale and to be accurate. All right. So that was originally it. And so basically 1 degree Celsius equals 1/100th of the distance between the boiling point and the freezing point of water. And that's what they did. They just took those two temperatures, divided up into 100 little units and said that's what that is going to be. All right. Now, where did Kelvin come from? All right. Notice it is Kelvin, not degrees Kelvin. I will probably forget and say degrees Kelvin because I'm just so used with temperature to put the word degree in there, but technically it's Kelvin. All right. If they learned more about temperature, they said, well, temperature has to do with your molecules and how fast they're zipping around, okay? All right. So if temperature is how fast your atoms are moving, then the coldest temperature you could ever get to is the temperature at which your atoms stop moving, because you can't get any more or less movement than stopped, okay? And they did some calculations, and they estimated that if you got down to negative 273 degrees Celsius, you would be all motion would stop. The electrons would quit spinning around, the protons, everything, the whole atom just shuts down, okay? And they said that's going to be 0 Kelvin, or absolute 0, because you can't get any lower than that. And therefore, there is no negative numbers. And that's one of the advantages of Kelvin, is that if you're doing calculations, you don't have to worry about if you have a negative temperature like negative 40 degrees or negative 273 degrees Celsius. It's a lot easier to calculate things because you don't have to mess with the negative numbers. So that's kind of an advantage of it. Now, just for the record, how cold is this? If you went into outer space, far outer space, where Pluto is, where it's just an ice ball out there because it's so far from the sun, it would only be like negative 100 and something degrees Celsius. Okay, so this is very, very cold. Now, we have never gotten anything absolutely to that temperature. We've gotten really close, within 1,000th of a degree. Okay, negative 272.9999999. Okay, but they can't get quite down to negative 273. It may not be possible. They think that it's probably not possible to get things to that temperature where they actually shut down. We don't know. The only times they've done it is in like a small little chamber with magnetic fields and stuff like that. And so for that time, when they did that, that little chamber was the coldest place in the universe, probably, as far as we know. We haven't found anywhere or any signs of anywhere being that cold anywhere else. Okay, and so that is very, very cold. But we've only been able to do it in small little chambers. We can't do it like a whole classroom or something like that. All right, so Kelvin has no negative numbers. And so if you want to change from Kelvin to Celsius, you would just add 273 to make it Kelvin, or subtract 273 to go to Celsius. So for example, in Celsius right now, the room being about 75 degrees is about 25 degrees. And so if you added 273 degrees to that, you could say right now the temperature is 298 degrees in this classroom. All right, actually that'd be 298 Kelvin. All right, so if someone asks you how hot it is outside, you can just blow their mind and do it in Kelvin and say, yeah, it's about 298, 300, something like that. Yep. And it would be true, but they may not believe you there. All right. So, if you have 0 Kelvin, if you went up to, let's just say 1 Kelvin, okay, then that would be negative 272, because we're coming closer to 0 with negative numbers, degrees Celsius. All right. In other words, if the temperature goes up 1 Kelvin, it goes up 1 degree Celsius. So a temperature increase of 1 Kelvin is equal to a temperature increase of 1 degree. The amount of temperature change is the same. Okay, and that's why you can just add 273 or subtract 273. The numbers are just different, but they'll go up the same amount. If one goes up 2, the other one goes up 2. It's very nice that way, at least. All right. These others we're going to go through fairly quickly. This one we will not talk about much. You may have in chemistry class. If you want to know how much you have of something, the measurement for that is a mole, M-O-L-E, just like the little furry animal that digs in my front yard and tears it all up. It's called a mole, and the abbreviation is so helpful. It's MOL, so you save one whole letter by using the abbreviation. So I don't know if that's really useful. We just have so many things that start with an M, I guess. So MOL is the official abbreviation. We will not use that this year. That's the good news. No stoichiometry or converting moles to grams or any of that good stuff that you did probably in chemistry. And that's just how much you have of something, the number of atoms in a substance. All right. The electric current, if you measure how much current is flowing through something, the unit for that is the amp or ampere. Technically it's ampere, it's named after a French scientist, but usually we just shorten it to amps, and the symbol for that is a capital A. Alright, and then the last basic unit is luminous intensity, which basically just means how bright something is. It is called a candela, or CD. Now, it's kind of interesting with light bulbs in the United States. We started measuring them by watts, which is how much electricity or power they use. Okay, and so we used to have 60-watt bulbs, and that worked fine until we came out with our new twisty fluorescent bulbs and the LED, LCD, LED, I guess. Okay, the other light bulbs that we have now, and so they actually can give off more light, but they use less electricity. So what used to be a 60-watt bulb is now a 23-watt bulb. So they'll say equivalent to a 60-watt bulb, just so you know, oh, that's the same thing we used to buy. If we had originally listed light bulbs by how much light they gave off, then that would have been probably more useful. But for a long time, that was the only kind of light bulb there was, so it didn't matter if we used watts or not. Anyhow, on the light package, they don't usually actually use candelas. Don't ask me why, because that is the official unit, but they actually use lumens, okay, which are L-U-M-E-N-S, and still measuring how much light they give off. And so maybe in the future someday we will just have light bulbs that are so many lumens or candela rather than doing it by the wattage, but we shall see. All right, that's it for the second part of the notes. So if you will now go and answer the few questions at the end when I get them posted, and you'll be done. Have a good day.